Welcome. We will be starting shortly.
We will be starting shortly.
Welcome. I will be starting shortly.
I will be starting shortly.
Welcome to Microcontrollers with kingernorth. I hope you can hear me. I can't tell right now.
You can hear me. I can't tell right now.
I hope that you can. You can let me know in chat.
I hope that you can. You can let me know in chat.
And we're going to be playing today on episode 28 with the QTPY or the QTPY
by
Adafruit. It's the small microcontroller. We're going to use it with CircuitPython
and with Arduino today.
Sound bad. What are we getting today? Are we getting echoing?
What are we getting today? Are we getting echoing again, Walter?
Morning nachos.
Morning
Double
nachos.
echo.
Double echo.
I think I might know why.
So
you gotta figure out how to turn it off. Okay, did that improve anything? Is that? I'm hoping
Is that
going to be better.
I'm hoping that's going to be better.
Okay, let's try that. I made sure the microphone is off on
the other computer.
No way.
No, eh?
No, the document camera is off.
The document camera is off.
I will check.
The microphone on it. I will check.
Okay, let's try that. Is that any better now?
Let's try that. Is that any better now?
We're soon going to find out. I see it said now that it's good. No, still bad.
No, still bad. No.
I don't know where the second voice is
coming from.
I don't have. I only have one microphone.
I only have one microphone.
I just shut down the power to my speakers. We'll see if that's any better.
We'll see if that's any better.
This audio thing is getting to be a real pain.
This audio thing is getting to be a real pain.
Because I can't figure out what it is.
I can't figure out what it is.
Both are good quality, so it is a repeating.
So it is a repeating.
Audio input is set to there. Okay, I don't know if you can hear it now. I've actually changed one setting. Is there a voice? Double, single? Boy, this is getting really not happy. One voice. Okay, I think maybe we played with enough settings to get it to work. Hopefully that's going to be true. So, yay! Finally. You know, this XSplit, when it did its update about a couple weeks ago, what a pain it's been. But that's beside the point. Let's carry on with today's show. By the small microcontroller with CircuitPython and Arduino. So let me just show you what we're going to be using today. So we're just going to zoom in. And we're going to be showing you, I have a couple of them running right now. This one here is connected with Arduino. This is on the purple cable. This is actually connected and running an Arduino code. And it is running these lights on this particular strip here. You can see variable lights are coming on, and that's what we're going to program first. The second one over here is running in CircuitPython. And you can see the LEDs a little bit better because I actually have I have a filter over top of the light, so you can actually see they're going through a number of different sequences. I'll show you that program, but we're going to build another program with this one over here using this attachment board with the CircuitPython. And this will actually let us do an indication for distance. But let's talk more about these different chips that I have here. I have a whole pile of them here. Last episode I dealt with this Pico. Sorry about the scratchy. I'm not sure what to do about that, but at least it's a single voice. That's probably got to be better. So this is the Pico. This is the one that came from Raspberry Pi. This is the really nice board. Let me see if that setting has to be set on this screen as well. No, it looks like everything is set here. The same on both pages. So this particular board is the one I talked about last time. This is really cheap. This was like the $4 US a board. Doesn't come with the pins. You have to add the pins yourself. So you can buy it with pins usually for about $5, and then you have to solder them on. This is a really good, cheap board, but it's fairly large. This is the Cutie Pie that we're going to use this week. And I have a number of them here. I have 4 of them in the image right now. And I'm going to talk about the differences and get into the details with that. But I also wanted to show this one over here. This was the Trinket. This was the one we used before, and I did an episode on the Trinket M0. And this is a very good board. But there's some commonalities between all of these boards. First, they're all cheap. None of these are really expensive boards, which is really handy when you want to build a project. The second is they all use the same processor in the microcontroller. It's a Cortex M0 processor. This uses the Cortex M0. The Cutie Pie uses the Cortex M0, and so does the Raspberry Pi. It uses a Cortex M0, the difference being it has 2 of them inside the chip. It's a dual processor. So it actually has 2 of the Cortex M0 chips inside of it. So that's one of the differences that they brought out with the new Pico board. But other than that, they all use the same instruction set in CircuitPython and Arduino, which is really, really handy. So let me move some of these other ones out of the way. We don't need these. And we're left with these items here, which all involve the QTPY. So let's have a better look at what we're doing here. So I'm going to go over to my other camera, and I'm going to bring up some images. So the first thing we're going to do in here is we're going to look at some photos. And this is the QTPY in detail. Here it is nicely blown up so you can actually see it. It's going to be much easier to see. We have a USB-C connector on the end. So that's a little bit different. That uses the new round connector. And that was just a choice that they decided to go with, and I'll talk more about that when I show you the board and how it's connected with Arduino and with the CircuitPython. On here, we also have a number of pins on the side. We have a bunch of connection points. So we actually have a lot of digital connections. They have some stampings on the board that show you some default addressing. So we have like A0, A1, A2, and A3, which are analog pins. The SDA and the SCL are the I2C communication pins. That's default where they're connected. We have a transmit and receive, which is the serial port, same as the USB. We also have the SCK, M1, and M0, which are used for SPI communications. We have a 3-volt connection that comes through the regulator right here on board in the middle of the board, a ground pin, and then we have the 5 volts that comes from the supply, in this case from the USB. So we also have that 5-volt connection. On the board itself, it also has one tiny, and I mean tiny, little NeoPixel in the middle. So having all these pins as what they are by default for their communications or analog, we also have digital on all 11 of these pins. We can actually use these as digital inputs and outputs to make our life a lot simpler. Hey, good morning, Demonic. So he's in here, Death by Nachos, Felix, Walter, and whoever else is in here too, probably Brian and maybe a couple of others. Thank you very much for showing up. So we have all those chips that are available to us for digital inputs and outputs. So even though they're used for other purposes, we can change their usage as needed. Now I've added some other notes here. Things like capacitive touch. Capacitive touch are available actually on a lot of the analog pins, but only 6 of them. So A0 through A3, and then also A6 and A7 have built-in capacitive touch. That means you can put one lead coming out, you can touch it with your finger, and you can actually trigger the circuit that way. So they are usable for touch-sensitive circuits. So you can actually set them up and use them as a touch input, which is really, really handy on those particular pins. We also have a true analog output. So out here on A0, it's a mono channel, but we have regular sine wave output. So we can actually supply power to an amplifier and run into a speaker. Now the small class D amplifiers are for the small speakers, and we can run it because this is just a signal. It's not meant to drive the actual speaker. That takes more power. So you use an amplifier. And then that way you can actually have audio files playing out from this chip, which is really, really handy. We also have pulse width modulation output. Now, pulse width modulation allows us to do the fading on things like LEDs. That's what we use those for, different kinds of controls. So those are available from D2. They're not available on A0 and A1, but they are available from D2 all the way up to D10. So that allows us a lot of flexibility for hooking up things like NeoPixels. We can send signals out to solenoids. We can send fading signals just to regular LEDs. We can actually run speed control to motors, all of those kind of things, because we have the ability to use that pulse width modulation. This NeoPixel, I mentioned this very quickly. It has an address. It's D11. It's not on any of the other pins. It's strictly internal on the board, since there's lots of pins on this SAMD21 chip in the middle here, which has that Cortex M0 processor inside of it. And it's also got an enable pin. So if you don't want the light to be on, you can disable it by grounding or setting it low for D12. So it actually has 2 digital addresses. One to send the information out on, like you would for a regular NeoPixel. So you can actually set its color. And D12 actually for turning it either on or off. So if you're running a program, you don't want extra light coming from the board, then you can turn off that NeoPixel. Save yourself a lot of hassle. So this thing is quite powerful. It's got a lot of features on it. There's that little tiny, I'll point that out on the board to show you how tiny it is, and actually it's lit up on the CircuitPython board. Something else about this board, though, is the addition of this chip. We can add this chip to it, which I'll show you the physical size because this thing's small. And it can be added to the back of the board. This is the bottom side of the board here. We actually have a 5-volt pin and a ground pin here, so you could solder on wires here if you wanted to feed it from an external source. You also have this area here, which is normally empty, and you can add 2 megabytes of memory. Oh, it's gone scratchy again. Sorry about that. So it's actually allows you to add more and more. Hopefully the scratchiness will disappear. I'm not sure what's causing that. I'm going to have to work on that some more, I guess. And again, we have all the pins here where you can add the different pins to it. Now for today's circuit, this is what we're wiring up today. So this on the right-hand side is the Arduino setup. Basically, all I have is I have a strip of neopixels here. I have the 5 volts in the ground to supply power to the neopixels. And then I have 1 signal wire coming back, and I'm connecting it to M0 in the tag, but if you remember, that's D10. So that's actually going to be connected to digital pin 10. So we'll use that address when we're setting up our neopixels. On this side is my CircuitPython connection. Again, I'm using the exact same board. I'm using the exact same neopixel strip and connected in the exact same way, whether it's Arduino or CircuitPython. I've also added this other board in here. Now this is a VL6180 board. Basically what this is that we're using on this is we're using the proximity detection. This will also do gesture. So it'll actually measure gestures, whether you're moving up, down, left, and right. You can actually use it to control things. But what I'm using it for is I'm using it for distance. So it's actually got a little transmitter here and a little receiver here. So it actually sends out a little infrared light and receives it back here, and it can tell the distance because it measures it in time. Now this particular one is the older style board than what I'm using today. This uses the regular pins on here. The one I'm using is actually taking advantage of what's here on the end of this QTPY, which is called a stemma QT. It's a stemma connector. The stemma connectors originally came from SparkFun. But these are the miniature version, so they're the QT version. And the new board, which I'll show you, also has the ports on the edge of the board as well. So it's just a jumper cable to plug in. There's no actual wires connected to the board. Those 4 cables, those 4 wires are actually all in one cable, and they just plug from here, from the QTPY, right directly into this board to make connections basically foolproof, because there's no way to cross the wiring on it. It only connects one way. So that's what we're going to be working with. And this is the board that we're actually using. They call it the APDS 9960, which is the replacement for the VL. It's the same chip. And here we can see the 2 parts of the actual item. And here's those connectors on the end. And it doesn't matter which end you plug into. There's no in and no out. It's just parallel through. So you can actually connect more I2C devices. This is going to talk over that IC2 protocol. And this has everything on it that needs to be here, including resistors. There's a regulator, voltage regulator here, so this will work with 3 volt or 5 volt. It regulates it down to 3 volts anyways. That's what VIN is. If you only had a 5 volt system like on the Arduino, this will work fine on the Arduino. It'll also work on fine with all the boards that only use 3 volts on the system. So I don't know why the scratchy's coming and going. I really don't know what's going on with that. But we'll see if we can't figure it out for next show. Basically, that's everything that we're using on that board. So let me turn that off. And what we're going to do is we're going to set up now to run the Arduino code. So I'm actually going to turn off my CircuitPython screen here. I'm going to adjust a few things in the picture once I show you a couple of parts. So let's get my desktop region up. There we go, my Arduino screen. Let me turn off my CircuitPython screen. So this is going to be where we're going to build our code today. So let me just get a couple of items out of the way here. This one here, to make it less distracting, I'm actually just unplugging the neopixels, the signal wire going up to the neopixel. This I'll leave connected. I wanted to show you this. This is the board. That's the size in my hand. Now, my focus is going to, let me unlock my focus there. You can see that's a really small board. But it has that USB-C connection on the end of it. Now, a lot of our cables that we use for USB use this micro B connector or micro C connector. This is an adapter. It's USB-C on one end. It's got the micro C on the other end, and basically you just plug it in. Now the beauty with this USB-C, it doesn't matter whether I plug it that side. You can see there's the USB symbol here. I can unplug that, flip it over, and plug it in, and it works just as well the other way. So normally one of the biggest problems we have is when we're doing this kind of stuff. Let's see if it'll focus again. It's not being happy about focusing. Come on. I'll do that and then bring it back. I might be just a bit too close, but anyways. What we have is, this is, on the end of this has actually got a bit of a connection on it. I don't know if it's being picky on focusing at the moment. But that time, if the cable wants it and wants to flip over your chip when you're working on it, you just take the USB-C out and turn it over the other way with the cable plugged into it like I do here. So it sits nice and flat. It's happy. Now, on the back side of this chip, we see those 8 little pads in there. Let's see if I can get... If I get the angle right. Well, there it goes. So we have 8 little pads on the back. And on the back of that, I can solder on a chip. I've done that on this one. And that is a small chip. To give you an idea, this is a package that I get with the chip. And I'm using a small pair of tweezers. Let me just dump that chip out of there. Turn that over. There's the size of that chip. That little tiny chip. It is small. So, you figure it out. You go to the tip of your finger. There's on your tip of your finger. That is a tiny chip to be soldering on, but can be done. And I just used a soldering iron to solder that, so you don't need anything too special. I'll put that back in that package. I'll close that up later. And we're going to zoom in on this, and we're going to have a better look. And in fact, I'm going to try and tilt this a little bit to make it easier for you to see. And I can get those out of the way. And what I'm going to do, this is a neutral density filter. What this does, it allows me to put something on top of here. If we can get everything to cooperate, which is not always easy. But now we can actually see the individual pixels. And let me just bring that in a little closer. So there we go. We can actually see the strip. We can actually see this strip down here. We can see the individual LEDs. And this is what we're going to do on the NeoPixels. We're actually going to program this using Arduino. So we're actually going to build up this code. And we're going to see what we can come up with here. And we're going to run through a couple simple steps. And I'll download it to this chip and we'll make the changes. So when we're starting, we always start with a new file. First thing I like to do on here is I want to save it. So we're going to do the same thing we did before. We're going to go File, and we're going to hit Save As. We're going to go out here. It's in my Arduino section. I'm just going to come up in here to Documents. I'm going to go to the Electronic Shows. Here's our QTPY at the bottom. And basically what I'm going to do in here is I'm going to create a new file name. So this is live A for Arduino. So this is our Arduino code. You can't see that at the bottom. You will see it in the file name change, and it says live A. So that's all I've done is create the file name live A, just so we have a starting point. We always want to throw this couple of comments here at the very beginning. So this is just very simple. Test code by, and then you're going to put your name in, so we always know who the author is. And I'll let you know that I'm basing this on an example that's based from Adafruit. So you could build your own code. I'm just keeping it simple to get us going, and I'm going to break it down into smaller steps. So that's what I'm doing here, test code by me. And then we're going to include any required files in here, just like we always do. So we're going to include any helper files. Let's put the L in there. Okay, and the file that we're going to add in here is going to be the NeoPixel driving file. So we're just going to do it the way we've done before in our previous programming. We're going to use an include statement at the top. And this include, we're going to include the file called Adafruit _ NeoPixel. Now, if you didn't remember that name or have it written down somewhere or something else, don't worry. Remember, there are other ways to get this. If we needed to, we could have gone up here into the sketch. We could include a library, come down here to the libraries, and what we would do down here is we would look for the Adafruit NeoPixel. And if we selected that, it would basically type that line in for us at the very top of the file, and then we just move it to the location we want. So we actually have more than one way of getting this, so you can actually grab it right out of your listing at the top, which is part of Sketch. So up here, if I bring down that window just a little bit, there you go. You can see there's that word Sketch. So all I did was come down here to Sketch and then include library. And then continued all the way down here until I got to that one that said NeoPixel. So these are all libraries I've installed. I've talked about that before. Not a big deal. If you need to add libraries, you just browse for a library and search for it through the Arduino software. So this is what we're going to do. Now the next thing we have to do, and once we've done this, is we need to create that NeoPixel object so that we can access it in our program. So we're going to go in here, and this is create the NeoPixel object. And to do that, we're going to use some code. Luckily, what you do with this is normally you find out a lot of this by running an example file, which there are example files for these out there. But I need to do a few things. I need to define how many NeoPixels I'm using on this strip, and I need to define where I'm going to connect them, to which pin. So I'm just going to use the word define. This is the same as using integer equals, except I don't have to put the semicolon at the end. And I'm just going to put in my neo pin, and I'm going to set it to a value of 10. So that's where I've connected it to D10 on this board. So I connected it to that digital 10 pin. And then the other define I'm going to do in here is I'm going to set how many NeoPixels I have. So I'm going to go define, and I'm going to go for my pixel number. Pixel num, and I'm going to set that to 8. This particular strip that we're using here has 8 NeoPixels on it. So we're going to go ahead and do that. So we've done that, and now we're going to do the rest of this, and this is done with the Adafruit _ NeoPixel, which is the name of the helper file. And you can see it matched in color once I got it spelt properly and in there. And then I'm going to give it a name, and I'm going to call it Pixels. This is the name you give it at this point. You could call it, lights. You could call it my lights. You could call it whatever you want. You're welcome for the filter. I thought of that about 10 minutes before the show, and I remembered I had these filters. And that's a neutral density filter, by the way, Walter. So I'm glad to hear that. Clear, scratchy, clear, scratchy. I don't know why it's going back and forth, but welcome, Bruce. Welcome to the show. So we're going to put in here, now the one thing we have to do is we have to include the pixel number. We created that as a variable in case we use a longer strip later or a shorter strip. We can change the length of how many we want in one place, and it'll adapt it in the program. We're also going to set up the Neo pin where we're going to connect this. And then we're going to put in some information that it likes for this. And this is basically, it's going to be the Neo GRB. And we're saying it's going to use that. And I know this is getting really wide, so don't worry about that too much. But this is all in examples for you too. I'll show you where you can get some examples, like this one I'm using here. And it runs at 800 kilohertz is what it's doing. So it's all running there. Put the bracket at the end and a semicolon. And when I hit the next line, you see it actually scrolled off the page. So very shortly or very quickly here, Adafruit NeoPixel, that's the name of the helper file. Pixels is the name I've given it, so that's how I'll call up the pixels in my program. I'll call them pixels. The number of pixels being used, the connection pin, where it's going to be connected, and then the information about the NeoPixels. And it tells me that they're Neos set up as green, red, brown, blue in the coding. Sometimes this is RGB, sometimes it's GRB, sometimes it's it can vary. So you have to watch that. And then we're just setting the frequency of how fast we're going to send the streaming information out to the board. It will accept a number of things. 800 is a good number. 800 kilohertz is a good speed for those NeoPixels. So there we are. We've created the object now. The next thing we would add in here is any other variables we need. So here you can define any required variables. So we're going to put those in as we figure them out. There's going to be a few, and we'll add them as we go. Now in our setup, the setup is basically anything that you want to run once. So all we're going to have to do in here, we're just going to highlight that out because I'm not going to worry about a comment in there for the moment. And we're just going to talk about the pixels. And I'm going to go pixels dot begin. And it's a function. So it runs up a subroutine called begin from the helper file is what it's doing. And basically what this one does, it tells them to turn the NeoPixels on. It says, hey, let me use the NeoPixels. So that's the first part. The next part is we're going to come out here and I'm going to tell it to clear any data that's out there. And I'm going to put in the word clear. And again, this is a function. So I'm going to say, turn on the strip, set all the lights to off. Basically, I'm just going to clear all the data in them so there's no lights coming on. And then I'm going to add one more thing, which I don't have in my other example, and it works anyways. But I'm going to go in here and I'm going to type in pixels show. And I want to include this one because this is a good instruction to add as well. And again, it's a default instruction as part of this helper file. Show means send this data to the NeoPixel strip now. So it's not waiting for anything else. It's saying, hey, let's take that information and let's send it out there. So what I've done is I've turned on the NeoPixel strip so I can use it. I've enabled it. I've cleared the data in there to set all the NeoPixels to off, basically, or black. And then what I'm going to do is I'm going to say send that data out to the NeoPixels. That will update the NeoPixels so they'll all be turned off. And at this point, we can actually stop this program. We can see there are NeoPixels on. In theory, this should work. So let's go ahead. I'm going to verify my file first before I try to send it. Down here at the bottom, it says it's compiling the sketch. As long as I didn't make any syntax errors, like put in or forget a semicolon or add extra code that's not properly formatted, it should verify just fine. And this is good to do it in small steps as you're going through so that you don't end up with a bunch of mistakes at the end and have to figure out where all these mistakes are. You do it in little bits and pieces. You can see the first time through, it takes a while to validate this code. You know, don't forget this computer is doing other things, but that is a long time to validate the code. But it came back and it says done compiling. And actually, if I push this window up just a little bit, In the black area there is where any errors would show up, any printing down here, and there is no orange print down there, so it's all good. It's happy. So I could go ahead and download this, and what it'll do, it'll turn those NeoPixels off. We're not turning any on right now, we're just going to do it. So I'm going to go ahead and tell it to upload, which it is going to compile again, which should not take as long. In fact, it says compiling sketch. There it goes there, and it says uploading it, and we should see all our NeoPixels shut off here in a moment. And there they did, they shut off. So they're happy. It did exactly what we told it to do. So that's the start of our programming. Now what we're going to do is we're going to set up a little bit in the main program down here in the void loop. And what I'm going to do is I'm going to put in a counter. So I'm going to say for, and I'm going to put in here, and I'm going to put in a term now that's just called count equals 0. So I'm going to start with a counter that's at the value of 0. I'm going to say as long as the count is less than the number of pixels. So I can go in here to my pixel num. I set that value to 8 up above. So I'm going to set num. I'm going to set it down to there. And then I'm going to give it here, and I'm going to go count. And I'm going to say plus plus. And then I'm going to put in a brace. And it'll give me an open and closing braces and inset me a little bit. This is now a loop. So what I've done here is I've created something that says, hey, for count equal to 0, so that's my starting point for the variable called count. Oh, wait a second, I just created a variable. I have to define it. I said define any required variables, so let's do this. This is going to be an integer because it's just numbers. So I'm going to go integer count equals 0, semicolon. I'm going to give it a default value to start the program. So down here, it's going to set the count equal to 0. It's going to say, as long as it's less than the number of pixels, do whatever's inside these braces. And at the end of doing what's in the braces, increase the count by 1. So it'll take count and make it from 0, and it'll make it equal to 1. And so far up to 7, it'll execute it. But when it turns it to 8, it'll come up here and say, hey, is it less than? No, they're both going to be 8. It's going to stop working. So it's going to do it 8 times. Even though it stops at the number 8, don't forget 0 counts as one iteration of the program. So it actually goes from 0 to 7. So that's 8 instances of it. So what we're going to do is I'm just going to go in here and I'm going to tell it to do a pixel. So I'm going to go in here, pixels, because that's my number. My number is going to be which pixel, oops, that's not a 9, that's supposed to be a square bracket. Square bracket, and I'm going to put in here the word pixels, or count. Got to get back on track here. So what I'm saying is here, on the first one, I'm going to go count, and that's equal to 0. So it's going to be pixels, position 0. I said there's 8 pixels. They're numbered 0, 1, 2, 3, 4, 5, 6, 7 for sending out code to it. So I'm going to say that that's what's going to equal to. And basically what I want it to do is I want it to set the color. And actually, pixels count, and I should be able to equal a color here. And let's make it the color red. You list them as RGB. So if I do this, let's see if this works right. This is not the way I have it written in the other program, but I'm going to try it. So I'm going to set these values out here to 255, because each color of the NeoPixel, the red, the green, and the blue, are adjustable from 0 to 255. So that says go to full brightness, 255, and basically what I want to do after that, I want to say, pixels dot show, just like I did up above here. That says update the information, so send that out. Take that 1 pixel and change it to this. So that's what I'm going to do with that. And if I do that, I'm going to give it a slight delay at this point. So I'm going to go and write in a delay. And I'm going to give it a time. And I'm going to call it delay time so that I can make adjustments to it. So I'm going to create a variable called delay time. So guess what? We're coming back up here in the code, and we're going to create another variable called delay time. And let's make that an integer. So we'll go back to the beginning of it, integer, delay time, and we're going to make that equal to, let's say, half a second. This is counted in milliseconds. So this is going to be 500 milliseconds, so half a second. So it's going to take a half a second. It's going to do this, and then it's going to repeat, repeat, repeat. When it's done, I want it to add another delay. So I'm going to add delay of delay time. So it gives me an extra half a second of delay. And then I'm going to say pixels.clear. So I'm going to turn them all off. And then I'm just going to say pixels.show to update it to make sure they turned off. And then I'm going to add one more delay time in here. And in fact, I'm going to show you something a little different with the delay time. So I'm going to go in here, delay time. And I'm going to use the times, which in computer is the Shift 8 key, or the star. And I'm going to say times 2. And I should spell delay time right, because that would make it a lot happier. And I'll put my semicolon at the end. And when I go down here, we can see there's my closing brace for the whole thing. I can shorten that up, get rid of that extra line. So here's my whole program down here. What I have is I have the count loop. I'm going to set 1 pixel to red. I'm going to carry on, then I'm going to change it to the next pixel, the next pixel, the next pixel, the next pixel, and so on down the line. When it's finished, it's going to delay for an extra half a second. It's going to clear the display, in other words, set them all to black, and then it's going to update that. It's going to wait for 1 second, and then it's going to start filling in the strip again. So let's see what happens here. Let's go ahead and upload, which first thing it's going to do is compile and validate the information I put in. If it doesn't like my pixels count instruction, it will tell me, and it didn't. So it did not. It did not like this pixels count. You see how it highlighted? So we had an error. And there is a reason here. So there's a couple of ways of programming this, and I'm just going to use, let me see. I'm going to go in here and I'm going to do it the way that they showed it in here. This should work, but I think in Arduino it's a little pickier. So let me get rid of the word count. I'm going to go pixels dot, and I'm going to use a predefined instruction that they have called set pixel color. This is where the using their files helps out. Let me delete that because I'm going to need to come down here and add that color back in. So I'm just going to put in my bracket, and this time I'm going to give it which number, and it's going to be count because that's going to be the one it wants to set. And then I'm going to say pixel dot capital C for color, and it is the American spelling for color. And then it says 25500, and I better make sure I put my other bracket in here. I had a starting bracket, so I need an ending bracket, and then I have brackets for the 3 numbers. And that's going to be pretty bright at 255, but that's okay. So now if I tell it to upload, it should validate that, and it should make it happier. CircuitPython is a little easier to set that color. This is the Arduino method. So it's compiling the sketch. There it goes, the green bar. It still doesn't like pixel. Pixels. Look how picky that is. I had pixel here. Pixels is my object. This is a great learning tool, and this is where we get to learn and see where the little errors pop in sometimes when we're doing things. So we're going to keep it nice and simple. And if it's happy with that, it is happy. It's now uploading. Once it finishes uploading to the sketch, there goes my red LED, my red lights in there, and it's doing what I asked it to do. So we actually got this program to work. Thank goodness for that. Now, I want to make one more change to this program that I think you'll find is interesting. And it's something that we've done before, and I'm going to add in a random number. So what I want to do with the random number is I'm going to create a couple of things here. So I'm going to change a little bit of the main program. For now, I'm going to have count is equal to 0. Count is less than whatever the case is. The red seems to be fine with the brightness as long as I have the filter on, so we're going to leave that on. I'm going to do a pixel set color, but instead of using the count for a fixed position, I want to add a random variable in here. So I'm going to create something called rand number. So this is going to be a new variable. So I'm going to have to add that to my variables list. And we're going to create something called random. And we're going to say it's going to be from the number 0 to a maximum of the pixel num. So in other words, 8. And because of the way it does things, it actually goes to 8 minus 1. So it's going to do it from 0 to 7. It's going to give me a number from 0 to 7. And then what I'm going to do in here, instead of count, I'm going to change this to random num. Random number, actually. So I'm going to go ahead and put that in there. And by doing that, I can go down here and I'm going to leave everything else the same. What I have to do is I have to go in here and I have to add that integer up here for random number. So I'm going to say integer random because that matches, it's actually random number. Let's spell it all the same everywhere we go. So it's rand number. And I can just put a semicolon because I don't care what the number is. I could make it equal to 0, or I can just leave it blank and it actually sets it to 0 by default. I could have done the same thing for count. So this should take care of it. What this is going to do is it's going to go through this again 8 times through the count. And then what it's going to do is it's going to set at random which neopixel turns on. So if I did this right, I'm going to hit this. So with one small change, I've added a random number. It is compiling the sketch, so it hasn't downloaded yet, so we're still running on the old sketch. There, it's finished compiling. It'll upload, they'll go black, and then it should go right into its program. And you can now see that the lights are coming on at random pattern. Now, if you noticed, not all of them came on. There's a good reason for that. Is because sometimes the same random number is being chosen twice. So there I end up, like, if we count them, there's 1, 2, 3, 4, 5, 6. We only got 6 out of the 8. That's 3. Oh, there's 4. We only got 4 that time. So because they're random numbers, they're not necessarily all going to turn on. Only if we happen to get all 8 in a string in a row will we get all of them on. But now it turns them on in random order. So we don't know which one's going to turn on next. So that's something that we can do with this, and we could utilize this inside of anything to make a blinking set of lights. Of course, we can change our delay times. We had it set for half a second. We could set that for a quarter of a second to make it quicker. We can change the delay at the end on how long it sits black by increasing or decreasing that value. So we can do lots of different things with this. And we can actually get into it. And one of the things that we do if we're trying to create like a sparkle effect, we do this very quickly. So instead of 500 milliseconds, we might do this in 50 millisecond remarks. So I've taken that code and I've changed that 500 to 50. I'm going to upload that, and we're going to see the one change that I made. All I did was take out one number. And by taking out that one number, once it compiles, this is where Arduino is slow. It takes a little while to compile. It's doing it. It's going to upload it. It's going to clear the values, but look at how fast those lights blink now. And they're all over the place. So think of how this could be if this was a string 100 long and you actually wanted to turn on them off at different times. And you can actually change this by changing your count. I use number of pixels. You can change that to something else. You could say, hey, I only want 50% of them to come on at the most. So you could say pixel num divided by 2 to give you that number. So if I set my pixel number to 100, it would only go through this count 50 times. Lots of operational changes you can make in here. So I hope that's interesting. So what we're going to do is I want to move on to the CircuitPython version. But that's the Arduino version for you. If you ever want these codes, you can always send me a message. Definitely do that. My contact information is in my YouTube site. So definitely do that if you need to get copies of any of these codes. So I'm going to go ahead and I'm going to move on out of here. I'm going to back this up just a little bit, because I'm going to take that out of there. And I'm going to bring this one over. Let me plug it back in. We can see it's still running. In the meantime, I'm going to disconnect the signal wire on the Arduino one. And I'm going to put that filter over top of these ones. And we're going to adjust this in the camera. In fact, let me just unplug the Arduino ones so they're not affecting it. And we're going to bring this board over here for us. That'll work. Maybe just something like, I'm just going to pin it in. There we go. I'm just going to hold it in place with that. It's not actually doing anything to it. And we'll bring it down in here. We can see everything that's on here. And that is going to affect me a little bit, but we're going to see how that in the program. Let's see if we can't do it like that, just for now. So this one here, we're going to do it a little bit different. I'm going to go ahead and I'm going to change screens here, and I'm going to go to my Mu window, which is my CircuitPython program. So this is the program that's currently running on the board right now. We can see here it's basic NeoPixel animation for the QTPY, which is what we're doing. What I've done in here, and let me just get my mouse in the proper spot. Here we go. At the top, we're importing the time, the board, the NeoPixel, and the Adafruit Pixel Buff, Pi Pixel Buff program. These are all helper files, just like we did on the others. Now, this program is directly out of the examples from Adafruit. The next one I'm going to show you is not. It's a highly modified version that I've created. So this one here, again, with the board, pixel pin, it's going to be set to D10. Pixel number is equal to 8. And then right here is where we create the object. Again, it's called pixels equal neopixel.neopixel. And then you've got pixel pin, pixel number, and then auto write is set to false, which means you need to put in the show statements. If you set auto write to true, every time you make a change, it will automatically update it, but we don't necessarily want to do that. Sometimes we want all the lights to come on at once and not have delays between them, especially if you're doing the whole thing. Down here, they've created a bunch of subroutines. One is for blinking. So this is a blink animation. So this is where everything tells it to blink. Then there's a chaser. This is the code that's required for chaser. Like I say, this is an example, so this is a big little subroutine. There's a wipe that tells it when it wipes the colors. Right now they're chasing. There's the wipe now going on. You can see the colors going across the screen. And then we have a rainbow effect. And then we have some predefined colors down here that they've set up. And they've actually named them red, yellow, green, cyan, blue, and purple. And basically purple is kind of a mauve. I guess it's purple, mauve. You call it what you want. And then what happens in here is here's the code. Basically what's in here, it says blink 5 times. So it says print blink. And I'll show you what that does because it actually gives us a feedback on the system. So we have blink and range, and it's going to be for 5. So that's like that 4, count equals 0, count is less than, count plus plus. So this takes the place of that. In CircuitPython, we use 4 blinks in range. So there's the object is blinks, and the range is we count up to 5. So it's going to go 0, 1, 2, 3, 4. And then we're going to blink it to the color red, and we're going to set it for a delay of 0.5, and that's going to be passed on to that blink subroutine that was up above. This one does the chasing and tells it what to do. And then down here is the fill. Just fill it with single colors. We have the white program and the rainbow program. So all they do is they call up their stuff. If I turn on the serial monitor here at the bottom of the page, it's probably not going to show first time. Let me try saving this, because it's been disconnected for a while. See if it'll save. Is it going to give me a hassle? It probably is. So what I'm going to do is I'm going to close that file. I'm going to go load. Let's see if we can't find that on the library. You can't see it, but I'm looking in the G folder for a file called code.py, which is this one here. And if I hit save, it says it saved it, and it's not bringing up the information at the bottom. I hate when it does that. It usually means I have to unmount and remount the drive, probably because I had the NeoPixels unplugged at one point. It's probably not happy with me. Let me just see if I can fix that. This is going to take a moment. Oh yeah, it's not happy with me. I probably should have ejected the drive. Windows is kind of picky this way. I should have ejected the drive because it looks like a USB before I unplugged it. So now it says it's been disconnected. I'm going to unplug my USB. The lights went out. I'm going to try plugging it back in and see if it'll be happy. It came back up as G. Since it did, if I open up the serial port and I hit save, it says it saved it to G. But I'm not seeing the update here, so it's probably not really doing it. So I'm going to turn off Mu for a second here, and I'm going to close and reopen Mu. This is the beauties of Windows. That's why I like programming with my Mac a lot of times, is it's less prone to these errors. It has its issues too, but it still works well most of the time. So I've reconnected here, and I'll turn that Mu screen back on. And if I open up the serial window and I hit save, it's not going to be happy with me for a while. So I'm hoping I'm going to see I can get the other file in there or not. What I want to do is I want to change to another file. And this is the one I want to do. And I'm hoping I can show you this. What I'm going to do is I'm going to go copy out of here. I'm going to go new, and I'm going to create a new file on my Mu screen. So let me close the serial port. I'm just going to paste this in here. I'm going to show you what I did. So before we save it here, I've created my normal disclaimer at the top and all my information. So this is just a information file for me at the top. So it says distance sensor with NeoPixel. So this is adding this extra distance sensor here. This checks for an object approaching and displays the results on the NeoPixel strip. This could be used to show that a rail car is nearing the end of a track. So if you're coming in, a lot of people know that I work with model trains. So for approaching the end of a stub track that's hidden, I can actually measure the distance and I can make the lights react according to that distance that's currently there. We'll see if it works. I'm hoping it will, without giving me too much trouble, because otherwise it wants to be rebooted. Include the required helper files. So I'm going to have time, board, bus I/O, because it's going to use the I2C, the Adafruit VL6180. That's the chip that's on that, even though it's the stemma board. That's the one we're using. The NeoPixel, import NeoPixel, and then we've also got the import Adafruit Pixel Buff, which is what we did on the other one. Previous program. So we're going to set up the I2C object. So I'm going to say I2C equals bus I/O I2C, and it's just going to use the default addresses on the board, the SCL and the SDA that are already predefined on the board, and the sensor is going to be the sensor I'm using. I want to set up the NeoPixel object, so again I set it up on D10, 8 pixels. Here's that long line that sets that up. And I've also set my pixel brightness down to 0.2 so it's not blaring out at full volume at me. Here's my colors. I've actually added 2 colors to this list. I've added orange from the previous file, and I've also added black. Black is just my way of turning them all to zeros, all the values to zeros. Then what I do in this one, this is the true loop. This is what runs all the time. There are no subroutines in this one. So in this one here, I have while check, and it's going to check for the distance from the sensor. So it's actually going to get the sensor information. and it's going to print that into my serial monitor. It's going to give me a distance, pardon me, in millimeters. Now, the distance ranges from 0, which it never gets to 0. You can only get down to about 10 accurately. And you can go up as high as 255 millimeters, which is about 10 inches. For those people that are from that don't understand metric, so it's about 10 inches of distance. So this sensor here measures from almost touching to 10 inches away. And what I've done here is I've just set up a bunch of if-else sections here. If the area is clear, in other words, there's nothing within that 200 millimeter mark. If it's over 200 millimeters away, then all I do is I take pixel number 7, and this is where I was trying to do it in the other one, and I set it to the value of green. So it goes up there to my green value, fills in the 3 numbers, and it's happy. So it goes in there, and I actually highlighted out pixel show because I don't need it, because I have the auto on. So since I have the auto on, I turn these functions off. So all I do is turn pixel 7 and I turn it on. And then when it's less than that distance away, or if I'm under 200 millimeters away, I turn it to black, which means turn off the green pixel. As an object approaches, I measure the distance from 201. So basically, when it's less than 201, which is 200, to greater than 100, in other words, from 101 to 200, I react on that. And what I do is based on, as the distance grows, I start turning on the pixels. So from the green end, I go to the next pixel, I turn it to yellow. I take the next one, I turn it to yellow. Then the next 2, I turn to orange. I'm getting closer to my stopping. And if I'm outside of that range, I just set them all to black to make sure those 4 pixels turn off. Then if my object is less than 101 millimeters, so it's 100 millimeters or less, I start turning on red lights. And I have 3 pixels left on this strip. So I use the 3 pixels and set them to red when it's in that range. And again, I'll turn them off once we increase the range back further. So we can actually use this. And then at the very end of all this, this is where I tell it to pixel show, and I do my time sleep. So it's happy. And it seems to work really fine. This little happy is only a 1/10 of a second delay. In CircuitPython, our delays are measured in seconds, not milliseconds. So this would be the same as in Arduino. This would be 100 because they use milliseconds. So this is everything that we're using in here. I'm going to see if it'll save properly. I'm going to tell it to save. I'm going to go to my G drive, which is on here, and I'm going to say to code py, and I'm going to overwrite that code. And if it worked, it did. Look at that. It still wrote it. Is my serial monitor working now? I don't know if it did or not. I'll turn it off. Doesn't matter. So let's go over here to this. So right now we can see, because of this, I'm going to move my sensor out into the open now. So let me take that sensor and move it out here where it's clear. So you can see that that sensor is not picking up anything because nothing is near it. I'm going to bring my hand in and I'm going to start moving in on it closer. As I get closer, you can see those yellow LEDs are starting to energize. Then it'll go to orange. Then the red ones will start picking up. And I can use the red to indicate when I'm all the way close to it. So I can jump in at any point and I can turn on lights. So again, as I approach, my LEDs, my Neos light up all there. If I get to 3 red, I better be stopping my train. And as I pull away from the sensor, we're going to see that they light up in blocks coming back out until finally I'm far enough away that it goes green. So I hope that was easy enough to see. We'll put that back on there again. As I approach, there it is there. Next one. I'm trying to move slow enough that I can see each one move in. Hopefully the person who's running the train is slowing down at this point. There's the first red. You're almost at the end, near the end. Hey, let's go to a full stop. You're as close as you should be. And as long as that's the case, when he pulls back out, as he's moving out, he'll get the different sections light up until he finally gets a green, telling me my track is clear. So that was it. That's what I wanted to do with that one. Again, these programs are going to be available if you want them. Just let me know. Send me an email or a note through YouTube, or you can send it to my email that's part of my on my site as a contact information. I'll be glad to help you out with that. But that's what I wanted to show you. I wanted to show you how to create some simple code. We were able to play with it. You saw in the Arduino, it's a little different setup than it is in the CircuitPython. CircuitPython, you can make changes very, very quickly because it doesn't take hardly any time to download. But the Arduino does take a lot more time to download because of the way it compiles each time. But it has to because that's the way the language is written. Both are still relatively simple to use, easy to make changes. And that's what it's about. So I haven't seen any other questions come up. We talked a lot about how the voice has gone in and out. I'll have to see what's going on and look up some information for that and see if I can improve that. But I think that's going to wrap up our show for today. So I'm looking forward to it. I'm not sure what I'm going to do 2 weeks from now. I will figure it out and we'll talk some more. Make sure you can subscribe to the YouTube channel if you haven't done so already. You'll get notices from that if you turn on your notices. You can also connect to my YouTube channel, my Twitter channel. So here's the link for that. So I basically have Twitter is @kingernorth. You do that. I usually send out a tweet 1 or 2 days before the live show, and then I usually send one out approximately an hour before the live show, just as a quick reminder. YouTube, of course, is youtube.com/kingernorth. If you didn't look it up that way, if you're watching this later, I really appreciate it. Please send code. You always ask for a code, I know, but I only have Arduino code unless you want to learn the CircuitPython as well. Walter, I'm not sure which. Anyways, everybody have yourself a great weekend. Have yourself a great week. We're going to be doing this again in a couple of weeks. Like I said, I'll figure out between now and then what I'm doing, and I will post that in a tweet when I figure it out. If you have a topic that you want to see that you think involves this, send me a message. Let me know, either through Twitter or through YouTube or on the contact information to my email. And if possible, I'll see if I can do it. If we can make it into an hour-long show. All right. Until then, take care. Everybody have fun. Stay safe. Enjoy your electronics and however you decide to use them. Until next time, this is Kingernorth with microcontrollers from Kingernorth. See you later. Bye now.